In this video, we'll be discussing experiment 14, which focuses on the rates of chemical reactions. And in particular, what we're going to be working with today is the iodine clock reaction. So chemical reaction rates are something that you covered in lecture, and we're going to review some of the main topics that pertain to this experiment from your lecture at the beginning of this video. And then we're going to look at how we can develop an experiment to measure the reaction rate of a chemical reaction. So this graph is something that you looked at in class, and this shows the relationship of the concentration of products and reactants. So this is reactants and products as a function of time. And that's what we're really getting into when we talk about reaction rates, because a reaction rate is a measurement of the change in concentration of a product or a reactant with respect to time. So that's what a reaction rate is. So if you take a look, we start this graph, we start with 100% reactants and we start with no products. And then as time goes on and the reaction begins to proceed, some of our reactants get consumed, and by stoichiometry, we must therefore be producing a stoichiometric amount of products. And then we ride along this graph, and you can see that there's a consistent relationship across the entire graph, and that relationship is the stoichiometry of the reaction. So as we use up reagents, we must be making products. Now, the question is how do we quantify how quickly this reaction is going? And really what we need is two things. We need to know how much the concentration is changing, and we need to know over what period of time did it change. So we define reaction rates as a measurement of the change in concentration with respect to time. And therefore, the units are going to be in units of concentration and in units of time. So molar per second. So now there are two ways that we can measure this, and one is not one that we use very commonly. There's the average rate, and then there's one that we're more interested in, which is typically what we call the instantaneous rate. But both are sort of instructive in order to understand this. So an average rate is exactly what it sounds like. If you want to find out how quickly this thing is going between any two given points, that becomes a relatively easy task to solve, because all you have to do, let's say we want to know how quickly is this going on average between this time and this time. Well, what we would do is we would take the x and y coordinates here, which would be the concentration and time. On the y would be the concentration, and the time would be the x coordinates. And we would take those two different points, and then we would just draw a line between the two of them and calculate the slope. So we would take y2 minus y1 divided by x2 minus x1, which would be the concentration difference divided by the time difference, and that would give us an average rate. And that would basically tell us between these 2 points, on average, this is how quickly the reaction is going. And that's useful. However, generally speaking, what we want to know is we want to know what the instantaneous rate is, meaning at any given point in time, like right here, for example, at this particular time, how quickly is this reaction proceeding? And that's going to be different. This particular point is going to have a different rate than any other point on this curve, because this is not a straight line. If this were a straight line, we could apply a linear regression to it, and then at all points it would have the same slope. But since this is curved, all points are going to have a slightly different slope, and that slope is going to be related to the tangent of the curve at that point. And the way that we figure that out is through the derivative of the curve. So luckily, we don't have to do very much calculus in this course. And we can use other methods like the method of initial rate to quantify the rate of a chemical reaction. And we're going to talk about what the method of initial rates is in just a second. So now the next question in terms of concepts is what experimental parameters might affect the rate of a reaction? So how can we speed up or slow down a reaction in time? And what we have to remember is that reaction rates depend on what we call collision theory. Now, there are several theories that pertain to chemical reactions and reaction rates, but collision theory is one of the earlier ones and one of the more significant ones for general chemistry, because it explains reaction rates in the context of the collision of molecules or atoms that are taking part in the reaction. And what the collision theory basically says is that the rate of reaction depends on how frequently these atoms or molecules, how frequently the reactants collide, and how many of these collisions have enough energy to result in the formation of the activated complex. So the activated complex is basically the a sort of a pseudo transition state that you get up to, and it's the highest point in energy between the reactants and the products. And this is some kind of complex that looks a little bit like the reactants and a little bit like the products. And when you get there, this complex is either going to break apart and form products, or it's going to break apart and go back to the reactants. So collision theory says that the rate will obviously increase as you have more atoms hitting together, meaning more atoms, the more frequently they collide, that's going to lead to this activated complex forming, and that the collisions have enough energy to get you up to the energy of the activated complex. So you learned about that in lecture, and that's just kind of a review. So knowing that this has to do with collisions, let's talk about things that can affect the collisions of molecules as we understand this from things like gas laws. So temperature is one of the most obvious things that we have, because we know from gas laws that the temperature is the measure of the average kinetic energy of the molecules. So what you can see is in this little depiction here, as you lower the temperature, the molecules move relatively slower compared to a sample of molecules or atoms at a higher temperature. So you can see that the average movement of these is higher, and because they're moving faster, they're going to collide with a higher energy. So temperature will lead to, as you increase temperature, it will not only lead to more collisions, but it will lead to more energetic collisions. So we expect that increasing temperature will lead to an increase in reaction rate. Now, concentration is another one that's really significant here, because when we think about concentration, this is basically how densely packed the molecules are in air or in solution. It doesn't matter what the matrix is. But if we want to have collisions, the more densely packed these molecules are, the more likely they are to collide with each other. And therefore, that should lead to a more likelihood of it forming an activated complex. So concentration is really important, and we would expect that as concentration goes up, we'll get more collisions, and then that should lead to a higher rate. And then there's one other really important one, and this is one that we focused on in the context of reaction rates, but more so in the sense of this concept of activation energy. So activation energy is defined as the energy that's required to get to the activated complex. It's basically the energy that's required to get the reaction over this hump and to products. So there's some amount of energy that's required to reorganize the bonds, to make and break bonds, that we have to achieve in order for the reaction to move from reactants to products. So that's what activation energy is. And what a catalyst does is, instead of changing the kinetic energy or the concentration, this changes the pathway. So in essence, what this does is this catalyst lowers the activation energy by allowing the molecules to go through a different sequence of steps than they would just through random collisions, that allows for the reaction to proceed at a lower energy. So this kind of speeds things up in the sense of not requiring as high of a temperature. So you can run the reaction at a higher rate, but at a lower temperature. Now, there's a couple of different ways that this can happen, right? So an enzyme can work by taking a substrate like maltose. It fits into a specific pocket on the enzyme. And then because this pocket brings the molecule into the right configuration for this, this bond between these two glucose molecules to break, that allows for a pathway that's different from this just spontaneously splitting in solution, for example. So that's how enzymes work. They have this lock and key model that allows for a lower activation energy. Okay, so let's talk a little bit about the method of initial rates. So we learned in class that when we have a reaction like this, A plus B goes to C plus D, we can write a rate equation for it that's a general rate equation. And we know that the rate is going to be proportional to the concentrations, whereas the concentrations increase, the rate should increase. And that's assuming that the reaction depends on those concentrations. There could be times where a reaction rate does not depend on the concentration at all. We would say that would be a zeroth order, meaning there's no effect. But in general, the reaction rate should depend on at least one of the concentrations of the reactants It may not depend on more than one, but it should generally depend on one, unless the reaction is catalyzed by some kind of enzyme, in which case the enzyme concentration may determine the rate of the reaction. But in general, for general chemistry, the reactant concentration should play a role in the rate. And we can write a general rate equation by saying that each concentration has its own order, and the orders in this case are x and y, and that tells us how significant that concentration is in determining the rate. So we can have 0th order, 1st order, 2nd order. It's rare to see things like 3rd orders, and you can also see things like half orders. So there you could have an order of a to the 0.5. That's a possibility also, and that just depends on the mechanism. So when we write this general rate equation, we also have to have a constant that relates the concentrations to the rate, right? Because we have to think about units. So the rate is in units of molar per second, and the concentrations are in units of molar. So we have to have some kind of constant here that allows us to go between the molar per second of the rate and the concentrations in molar. And this will always have units of per second in it, and that allows us to get the molar per second from the rate. So the way that we write a general rate equation is we see that there are two reactants here. We have reactant A and reactant B, and they're going to C and D. So we know that the rate could possibly depend on A, and it could possibly depend on B. So we must include both in the general rate equation. And we use these unknown orders of x and y to indicate that we don't know what the reaction orders are. So we have to do something to figure out what these orders are. And we need data to get this. We can't just use the stoichiometry, because as you learn in chapter 14, the mechanisms may or may not have both of these compounds, both of these reactants, in the rate limiting step. So you learned about rate limiting steps and reaction mechanisms as you were going through the rate chapter. So we don't know, if we don't know the mechanism, we can't make any suppositions about what the x and y are, even if we know the stoichiometry. Only if we knew the rate limiting step could we say something about those. But in just a general reaction expression, we can only write a general rate expression. So then the question is how do we develop an understanding of what the x and y are? And we use something called the method of initial rates. And what this is we basically, just like it says, initial rates, we basically set the reaction up where there's a set concentration of A and B. It doesn't matter really what those are, but you want to try to select concentrations where you're in a range where the rate is not going to change these too much. Meaning when the reaction begins, it proceeds, but it doesn't proceed so quickly that that concentration is going to change dramatically from where it is in the window of your experiment. And I'm going to show you how we can actually set an experiment up to make this so that these concentrations don't change very much. And the reason why we don't want them to change is because we want to know at this instant where the reaction starts, what is the rate, right? So if these things change dramatically within the first second, then we really are not going to get a good representation. But if they kind of change a bit in a bit more shallow way, then we can kind of estimate that, as we begin to measure this rate, as this is changing, that this is largely related to this initial concentration that we're starting with. So in essence, what we're doing is we're taking an average rate right at the beginning here, and we're using that average rate to correlate rate with the concentrations. So as you can see, what we've done is we've set this up where we have concentration of A and concentration of B, and we have a couple of different setups, a couple of different trials here with different concentrations, and then we measure that average initial rate, meaning that an average rate over the first few seconds or few minutes of the reaction, and then we set up this table. And now what we want to do is we want to look and see how concentration affects the changes, how relative changes in concentration affect the relative changes in rate. So let's take a look at this and start to look at the effect of the concentration of A on rate. So we can select two of these. Trials. So we have trial 1, trial 2, and trial 3. And we can basically say, well, let's look at trial 1 and trial 2. In trial 1 and trial 2, we hold B constant. And that's really important because if we're trying to figure out the effect of A, we need to hold all other variables constant so we can just see, hey, how does changing A affect the rate? And then by holding B constant, we know that there's no effect of the rate on B. So using trials 1 and 2, we can look at and sort of begin to understand what's happening with A. So if we take trial 2 and we take trial 1, what we can do is we can say that that the relative ratio here, so we are in essence, we're doubling the concentration. So we're going from 0.25 to 0.5. So when we take the ratio of these two, we get 2. And then we can say, well, if we double these, what effect does this have on the rate? So remember, when we wrote the general rate equation, we have A to some power, and we want to know what is that power. So if we take the ratio of the concentrations and we take the ratio of the rates, we see that the ratio of the concentrations is a factor of 2, and that the ratio of the rates, 4 times 10 to the minus 4 divided by 1 times 10 to the minus 4, is a ratio of 4. If you plug that into your calculators, you're going to get a 4. So the question becomes, when we have 2, to what power will give us 4? And in this case, this is a very straightforward example because the numbers are so round. We can see that the exponent has to be a 2. 2 to the second power is going to give us 4. So we say that x equals 2, and that tells us that the A is to the second order. So now we can do the same thing, but for B. So for B, what we want to do is we want to select 2 trials where B changes, but A does not. And that's going to be trials 1 and 3, where we go from 0.01 to 0.02, but the concentration of A remains the same. So if we do the same setup, we divide the concentrations and we get a factor of 2. We divide the rates and we get a factor of 2, very neatly in this case. The data normally would not be this neat. I'm just doing this to kind of show you, just to kind of show as a demonstration. Normally these numbers wouldn't be as perfect, right? You would get rates that were actual, that had some actual numbers. They wouldn't be 1, 2, and 4. You would get, real numbers, as you're going to see as we do the experiment. But when you do the division, you should see, that these things are doubled or quadrupled or round ratios like that. So in this case, we can deduce that 2 to the first power must give us 2, or this is first order. So we say that rate is equal to K times the concentration of A squared times the concentration of B to the first power. So now we know that when we double the concentration of A, that will have an effect of quadrupling the reaction. And if we doubled the concentration of B, that would have the effect of doubling the rate of the reaction. Now, an important thing to also mention is how do we get the value of K at this point? Well, we can take any one of these trials and we can plug in the rate that we have, the concentration of A, the concentration of B, and then we can solve this equation for what K should be, including the units. And we have to remember that the units on the right have to work out with the units on the left. So whatever the units of K are, we have to make sure that that's going to give us molar per second on the left. So these are all things that this is kind of just a review from what you did in lecture. But this gives an overview of the method of initial rates and how we get both the orders and the value for K. Okay, so let's look at today's reaction. So in today's reaction, we're going to be setting up what we call the clock reaction. So in the clock reaction, we have peroxydisulfate, which is this compound S2O8 2-, and it reacts with iodide, I-, to give iodine in solution plus 2 sulfates in solution, and sulfate is SO4 2-. And just to show you what these compounds look like in terms of their Lewis structures, peroxydisulfite is this compound that has a sulfur bridged with 2 oxygens to another sulfur group. And you can see how this kind of breaks apart. If you break this bond, it's going to give you 2 of these sulfate molecules. So in essence, we're breaking the bond that connects 2 sulfates in the peroxydisulfate. So now an important question to kind of ask ourselves is, what type of reaction is this? We have several different types. We have redox reactions, we have metathesis reactions, and we've looked at those in the last few labs. We looked at those in the first semester in the first few labs. So now the question is, what type of reaction is this? If you look at this, you should be able to tell that this is not really a metathesis reaction because we're not exchanging partners and making precipitates or acid bases or things like that. The tip-off in this case is if you just look at the I minus, you notice that the I is going from an oxidation state of -1 to an oxidation state of 0. So the tip-off here that this is a redox, it's very easily seen by the iodide components. So if we were to write the formal charges, we can use the oxygen knowing that it's -2, and then we can kind of do the math. So we have -2 times 8 is 16 with an overall charge of -2. So that means that we have to have 14 positives. So if we divide 14 positives by 2, we get a formal charge of -7 on the sulfur. And we can do the same thing for sulfate. So over here we have -2 times 4 gives us -8. Since we have an overall charge of -2, that's going to give us a formal charge of -6. So what's happening here is we have a reduction of the sulfur from sulfur -7 to sulfur -6 in the sulfate. And we have an oxidation of the iodide going to I2 as the coupled half reaction. So we have the reduction half reaction and we have the oxidation half reaction. So that gives you a sense of, this is the reaction that we're looking at, and it's more than just something we're using to come up with a reaction rate. This is a reaction in and of itself, and it's something that we can analyze and understand, and it's something that we should think about for the quiz, that we can do redox reactions and measure their rates. So if we want to write a general rate equation, we would say that we have the general rate constant K, we have our two reactants, S2O8 2-, so we put that in, and we have I- as the other one. And we put X and Y as our orders because we don't know what those are. Even though there's a 1 and a 2 here, we can't use those because we don't know what the rate limiting step of this reaction is. So we just put X and Y. And our goal today is to determine K, X, and Y. So at the very end of this experiment, that's the things that you need to get. And there's going to be a lot of steps for how we're going to get them, but this is what you need, K, X, and Y. Okay, so here's how we're going to set this thing up. So this is one of the more complicated reactions to set up, but it's actually, when you break it down, it's not that bad. So in the end, what we need to have is we need to have some S2O8 2-, some peroxydisulfate, and some iodide, and we got to get those together into the same beaker, right? So in order for this reaction to start going, we need at least those two things. And that's what we're going to have. We're going to have a solution A that's going to contain the iodide, and we're going to have a solution B that contains the peroxydisulfate. So when we mix solution A and solution B, that's going to get the reaction going. So that's the most important thing to keep in mind. Everything else is sort of secondary to that, right? Everything else, because the reaction itself that's going to take place, we need to have some I- and we need to have some peroxydisulfate. And the I- is going to be in the form of potassium iodide. So that's going to be our source of I-. And we're going to put some volume of that into solution A. And we're going to have in solution B the peroxydisulfate, which is going to come in the form of sodium peroxydisulfate. And that's going to go into this second flask. Now we have to add some other things into this when we get this thing going. So when we set this up, in addition to the Ki and the peroxydisulfate that we need to get our reaction going, we're going to add potassium nitrate. We're going to add some 19 milliliters of that, and I'm going to talk a little bit about what that's for. Then we're going to add some other things like EDTA and starch and sodium thiosulfate. So sodium thiosulfate is the Na2S2O3. We're going to talk about what this does in a second. We're going to add EDTA. We're going to talk about what this does in a second, and we're going to add starch. Now, it turns out that, and so all of those extra components are going to go into A, and just the peroxydisulfate is in B. So now we have a beaker here that contains 30 milliliters of stuff. 10 plus 19 plus 1 plus 0.6 gives us, plus 0.6 and 0.4 gives us 30 mils. And then we have 10 mils of the peroxydisulfate in beaker B. Okay, so now what are the purposes of these other things that we have that are not in our reaction? And we're going to talk about that now. So the KNO3 is really important. When we mix these things together, we want to make sure that at all times we have the same number of ions in solution. So what we're going to see is that in this experiment, we're going to create a couple of different forms of solution A. We're going to change some things around. Most notably, the reason for changing things around is to change the concentration of I minus and of Na2S2O8. In the method of initial rates, we know that we're going to have to play with these concentrations in order to set up our initial rates table. So if we're changing these concentrations around, we're going to be changing the relative numbers of ions in solution. And what the KNO3 does is it makes sure that if we lower the Ki, or if we increase the Ki, we can balance out that change in the amount of Ki with some spectator ions that are also present, like potassium and nitrate. And that keeps the relative, what we call ionic strength, the same, regardless of whether we change the concentration of other things in the solution. And that's important because ionic strength can affect the way that a reaction proceeds. It can be important in the mechanism. So we kind of control that variable by adding in some spectator ions to make sure that the solutions are always the same. Now, let's look at what the EDTA does. So EDTA is what we call a chelating agent. It's basically a complexing agent that takes out any metal impurities that could potentially get into the solution, right? So all of these salts could potentially contain some kind of impurity that might mess up the reaction that as we have it, right? If we were to throw something in here that was redox active, that we don't want to be redox active, that could mess things up. So we put the EDTA in as basically a purifying agent. It's a chelating agent that removes any kind of interference that could potentially get in at our impurities from these. Now, the sodium thiosulfate and the starch are how we're going to create the clock. So we need not only our reactants in this case, but we need some way of measuring how quickly the concentration of these reactants are changing in time. So the sodium thiosulfate and the starch create the clock, and I'm going to explain how that works in a second. Now, the other thing that you would set up in this is not only are we going to put some sodium thiosulfate in at the very beginning, we're also going to take some test tubes and we're going to add some 0.4 milliliter increments of this sodium thiosulfate to these test tubes. And what's going to happen is we're going to add these test tubes in as the reaction proceeds. And I'm going to explain all of this in a second. But what you have to know is that in A, we have iodide, in B, we have peroxydisulfate, and then the clock is going to be formed by the sodium thiosulfate and the starch. So let's take a look at what that does. So as this reaction starts going, when we mix A and B together, the peroxydisulfate and the I- are going to start reacting with each other. And they're going to start to make I2. And they're going to start to make some sulfate. So it turns out that peroxydisulfate and iodide are pretty much colorless. We would not be able to tell that this reaction is taking place because pretty much all of these things, all of these species that are formed are colorless. We would have no visual cue to measure how quickly the reaction is going. We need some kind of visual cue to know how quickly this is going. So what we do is we add sodium thiosulfate and starch to create a reaction clock. So this is what winds up happening. When we mix A and B together, this reaction starts to make I2. And what the sodium thiosulfate is going to do is it's going to react with that I2 and bring it back to I-. So in essence, even though this reaction is producing I2, as long as the sodium thiosulfate is present and in there, we're never going to generate any I2 that's in the solution. All of that I2 is going to go back to I-, and it's going to start, and it's going to kind of go back into the beginning and start again as a reactant. So this S2O3 2-, the sodium thiosulfate we're adding, is going to consume all of the I2 that's produced and bring it back to its initial reactant. And then we make this other product, S4O6 2-, which we don't care about. That has nothing to do with the reaction. That's going to be produced, it's going to be in solution, but it's not something that we care about. What's important, though, is that the S2O3 2- gets rid of the I-. Now, for those of you who are in biology, you know that when you have iodine around and you have some starch, remember we've added starch into this reaction, the moment that we get some I2, we're going to form a dark blue complex. And this is something that's used in biology very frequently as a test for starch. You can add I2 and you'll get a blue complex. So now let's say, for example, we ran this reaction in just the presence of starch. What would happen is the S2O8 and the 2I- would begin to react together, and they would produce I2. And what we would see is the minute we started to make I2, it would react with the starch and make a blue complex. Now that wouldn't be very helpful because that wouldn't really tell us anything. All we would know is that in the minute we mixed the two together, it would turn blue because we were making I2. What's clever about this is by adding in the S2O3 the thiosulfate, the reaction begins, and even though there's starch there, because the sodium thiosulfate is present, that is removing the I2 from the solution. So what has to happen is we have to consume all of this sodium thiosulfate. Then as soon as this is gone, as soon as the sodium thiosulfate gets used up, the reaction can then start to produce I2 and we form a blue complex. So now let me show you what this looks like when we actually run this reaction. I think this is going to be much more telling for you to see it than for me to explain it. So let's kind of start to look at this. So what we have here is we have solution A that's sitting in our beaker, and this has our Ki in it, and it has all of our other things. So it has some sodium thiosulfate in there, it has some starch in there, it has some KNO3 in there for charge balance, and it has some EDTA. And then we're going to come in, and on top of this, we're going to add our solution B. Now this is our peroxydisulfate. And you'll notice that the minute that we added these two together, we don't get a color change. We're not seeing the formation of I2 yet. And the reason for that is because when the S2O8 reacts with the I- forming I2, the S2O3 that's in there, that's in the solution, reacts with the I to instantaneously reform I-. So we're not going to see a color change yet. So now what's going to happen is the reaction is going to proceed. In time, and as time is going on, let's kind of look at that. So as time is going on, we're making I2, and the I2 is reacting with the S2O3 2-. So in time, this S2O3 2- is being used up, and then when that's all used up, we're going to get a color change. We're going to get a color change to blue. So at this moment in time, we're getting a color change because the S2O3 2- is fully consumed. So when the S2O3 2- is consumed and becomes a limiting reagent, we can now, this reaction stops happening because the S2O3 is now the limiting reagent. There's none of it left. And so we start to make the excess product I2- in solution. And then that's going to instantaneously react with starch to form the blue color. Now remember those aliquots that we had of some extra S2O3 2- that we had? When we pour those in, that color goes away. So the minute we add the sodium thiosulfate back in, the S2O3 2-, the clock resets. Now, any I2 that was present is going to react with the S2O3 2-, and the solution is going to change back to colorless. So we're going to now proceed with a colorless solution until the S2O3 2- that we just added gets consumed. And you're going to notice that the time is about the same because we're adding roughly the same volume and the same concentration. So it turns blue when we add the next bit of sodium thiosulfate back in. It goes back to clear. And then eventually it's going to turn blue. And then we add it again. So what we're doing now is we're setting up a clock. And what the clock is telling us is that every time it turns blue, we've used up a certain number of moles of S2O3 2-, right? We know the number of moles by knowing what volume we're adding times the concentration. And with each addition, we know that as long as there's S2O3 in there, it's colorless. So from blue complex to blue complex, we know how many moles is consumed. So now we know moles and we know time, and we know we can start to get a reaction rate. Now that we know how the clock reaction is set up and we understand what's happening as we observe the color change in the clock reaction, let's take a look at how we can start to work toward calculating a rate. So we have the time issue worked out. We know that each increment of time between the color changes is when we consume the number of moles of S2032 minus. So in essence, that's kind of getting us in the direction of a rate, right? We have moles and we have time, so we're kind of getting there. The problem is that S2032 minus, the thiosulfate, is not in our main reaction. The main reaction that we're looking at, remember, the reaction that goes on, that chugs on throughout this whole process, is the peroxydisulfate and the iodide. So the sodium thiosulfate is giving us our clock, but we need to get our moles not in terms of the sodium thiosulfate, but in terms of the peroxydisulfate or in terms of the iodide. So now we have to do some stoichiometry to get that back. So in order to convert the moles of thiosulfate to the moles of peroxydisulfate, we have to use stoichiometry. So the first thing we need to do is we need to figure out, well, how many moles of sodium thiosulfate are we consuming between each of those color changes? So to do that, we know that each aliquot of the sodium thiosulfate is 0.4 milliliters, or if you convert that to liters, 0.0004 liters. And then the concentration of that is 0.4 moles per liter. So we can multiply the volume times the concentration to get the number of moles, 1.6 times 10 to the minus 4 moles. So what we know is that as the reaction is proceeding, when it turns blue, we've used up all of that 1.6 times 10 to the minus 4 moles, and now the I2 starts to get produced because we don't have anything to get rid of it. So we know that that's how many moles of the sodium thiosulfate are being consumed. Now let's convert that into the amount of peroxydisulfate that was consumed during that time frame. And we're going to do stoichiometry to do that. So we take our 1.6 times 10 to the minus 4 moles of sodium thiosulfate, and then we look at our ratio. So for every 2 moles of sodium thiosulfate, we consume 1 mole of I2. And this is our bridge. This is the link that allows us to go from here back up to our original equation. Because we know that for every 1 mole of I2 that's produced, 1 mole of S2O8 was consumed. So now we have a stoichiometric link between the moles of the sodium thiosulfate that were consumed and the moles of the peroxydisulfate that were consumed. So in essence, we're just taking this 1.6 and dividing it by 2, which gives us 0.8 times 10 to the minus 4, or another way of writing it would be 8 times 10 to the minus 5. So now, from this stoichiometry, we know that in between each of the color changes from blue, add sodium thiosulfate to blue, that is 0.8 times 10 to the minus 4 moles of peroxydisulfate. And so now we're going to look at this in terms of how we can come up with a rate. Okay, so now let's take a look at this in terms of what we just calculated. So what we know now is that when this thing turns blue, we've gone through 1.6 times 10 to the minus 4 moles of the sodium thiosulfate. And because of stoichiometry, we can relate that to the moles of peroxydisulfate. So now what we're going to do is we're going to plot the time with respect to the number of moles of the S2O8 minus that's consumed. So remember, each time it turns blue, we did the stoichiometry on the last slide. Each time it turns blue, we know that we've consumed 1.6 times 10 to the minus 4 moles of sodium thiosulfate, and by stoichiometry, we know that that is equivalent to 0.8 times 10 to the minus 4, or 8.0 times 10 to the minus 5, which is what I had on the last slide, moles of the sodium, the peroxydisulfate. So now let's take a look at what's going to happen with this as we kind of go on in time. So now what you would do is, as soon as you mix them together, that would be time 0. So you would start your clock the minute you mixed it together, because the reaction begins. And then we're going to wait for the first color change. Okay, so now we've had the first color change, and we're going to write down the time that we saw that happen, 128 seconds. So now we know that at 0.8 moles, we've had 128 seconds, and we get our first data point. Now we added in the sodium thiosulfate, and we wait for the next data point. So we got another color change at blue. We write down the time, and we're gonna plot that data point. So at 253, we had 1.6 times 10 to the minus 4. Now at 383, we had 2.4 times 10 to the minus 4. We add in our next aliquot of sodium thiosulfate, which is going to reset the clock. and then we get our next one, our next data point, and then finally we're going to get our last two data points. So the video will continue. I just threw them in here because we don't need to keep seeing it. But the key thing to remember is that every time the reaction turns blue, we've consumed 0.8 times 10 to the minus 4 moles of the peroxydisulfate, of our reactant. So what we've done is we've actually created a graph now where we know how many moles were consumed per given amount of time. And we can use this graph to get a slope, and that slope is going to give us the rate. So now let's talk about what makes a good graph. So you're going to be doing some graphing, and we're going to be talking about this in a little bit more detail in terms of the graph paper at the end of this video. But let's just look at what makes a good graph, because this is important. So when you're drawing your graphs for this experiment, you're going to want to make sure that your axes are labeled and that you include units. So you'll notice that my axes are labeled in time seconds, moles of peroxydisulfate. And for simplicity, I did this thing where I multiplied this by 10 to the minus 4 moles. That just tells me that each one of these increments is 0.5 times 10 to the minus 4, 1 times 10 to the minus 4. It just allows me to not have to write it out. But you have to remember, when you're doing calculations, you have to include the times 10 to the minus 4 if you're going to do this. Otherwise, if you're not comfortable with that, just simply write 0.5 times 10 to the minus 4, 1.0 times 10 to the minus 4, and that'll be fine. Another thing you'll notice is that if you look at the graph paper in the book, we want to make sure that we fill up the entire piece of graph paper. So you'll notice that if this were my graph paper, the data points fill up the entire piece of the paper. And we're going to talk a little bit more about that. I'll show you what the graph paper looks like at the end. So we want to make sure that we fill up more than 75% of the graph paper. Now, we need to get the slope out of this. So we need to get the slope of these data points to get a rate. So how do we draw a best fit straight line? Well, number one, we're going to use a ruler. And we're going to draw a line that gives an average trend through the data points. Remember, in this case, the data is pretty good. So this experiment gives pretty good data, and it's going to give pretty straight lines. When you're drawing a best fit straight line, it doesn't have to touch all the data points. So if your data points were kind of squiggled, we wouldn't want to see something that looks like this, meaning you draw lines between each data point. That's not what you want to do. What you want to do is you want to take your ruler and set it up so that the ruler is going through, on average, all of the data points, and you're going to draw a single line through all of the data points. That gives it basically the best fit through. So you can see here that I've done that. I've taken my ruler, I've drawn a line through these data points, and yes, some of the data points are slightly off. You can see this one is a little to the left. The data point is a little bit more right than the line is, but I've gotten sort of the best fit through all the data points. Now, there is one thing that's really important here. We have to remember that because this experiment, at the very beginning, we have to have some kind of starting point. And at the beginning of this experiment, no moles of peroxydisulfate were consumed, right? At time 0, when the experiment first begins, we have to have all of our peroxydisulfate is still there. None of it has been consumed. So we need to have this thing have a data point that is 0, 0. And we have to make sure that the line goes through the origin. So when you're drawing your line, you have to make sure that the ruler goes through the 0, 0 data point. And that's just because at the data point 0, 0 is not experimentally measured, but it's something it's theoretical, meaning that at time 0, no moles of the peroxydisulfate were consumed. So the line must go through the origin. All of the other data points, it doesn't necessarily need to go through it specifically, but it has to be a best fit through the rest of the data points. Okay, so in terms of calculating the slope of the line, so we don't want to, a lot of students tend to just go in and they take 2 of the given data points and they use those to calculate the slope. That's not what we want to do. What we want to do is we want to take 2 data points that are far apart on the best fit straight line, that are not actual measured data points, and we're going to use those to come up with our slope. So these are not data points. These are not the little green dots that were actual data points from the trend. And we're going to take them far apart. Now, the reason why we're going to take points that are far apart is because that's going to account for any error that's in your data pointing, right? So you want to make sure that you take 2 things that are far apart, because then any errors become small from the subtraction, meaning that the subtraction is going to be relatively large. You're going to get a large difference between them. Now, another thing that I want to point out is, well, why don't we take the actual data points themselves? And that's because there could be experimental error in one of those given data points. So by drawing the best fit straight line, we account for the average, or sort of the regression of all of the errors from these data points. So the slope is the way that we can calculate the slope is we can take the y coordinates from the two distant points and subtract them, and the x coordinates from the two distant points and subtract them, and then we can get our slope. So what this would look like is we have our data point here. You can see this is about almost a little bit below 4.5. You would measure that off using the grid. So this was 4.48 times 10 to the minus 4. And notice, even though I have the unit 4.5, I still write times 10 to the minus 4, because we know that these are in units of 10 to the minus 4. So I take 4.48 times 10 to the minus 4 minus 4.47, and this, I'm sorry, this should have been times 10 to the minus 5 here. So we take, I have it written correctly here. This is just a little bit of a typo. 4.48 times 10 to the minus 4 minus 4.47 times 10 to the minus 5. And then we divide that by 712 seconds minus 71 seconds. So I just picked two arbitrary points that were convenient for me, did the subtraction, and then we get our slope. Now, when I say convenient, what I mean is basically you're going to want to look where the line kind of crosses a grid crossing, and then you can use that as your arbitrary point. And then that way you can read the grid crossings right off of your data set. Okay, so now we have the slope. We did our subtraction and we did our division, and we get our slope, which is 6.29 times 10 to the minus 7 moles per second. What's important is that the rates don't have units of moles per second. They have units of concentration versus time, or molar per second. So molar per second is the same thing as moles per liter per second. So to convert the slope to a rate, we need to divide the slope by the total volume of the solution. And then that's going to give us a moles divided by liters divided by seconds. So in this case, this experiment is set up so that the total volume of all of our reactions are 40 milliliters. So we're going to take our slope, 6.29 times 10 to the minus 7 moles per second, divide it by 0.0400 liters, which is our total volume, if we convert milliliters to liters. And then we're going to get 1.57 times 10 to the minus 5 molar per second. So that's how we can convert the slope, which is in units of moles per second, to a rate, which is in units of molar per second. We have to divide by the total volume. Okay, so that shows you basically how we're going to work this for the first trial. So the data, you're going to get the data for the first trial, and you're going to create your plot. You're going to get your slope, and then that's going to tell you basically what's going on in terms of the rate. And then you divide your slope by the volume, and you've got it. Now, that depiction that I just showed you, I just walked you through one of the trials, right? But we need to build our initial rates table. So we can't come up with the rate constants unless we have multiple different trials. So the one that I just showed you, this was solution A, and this is one of the three variations that we're going to do to create that initial rates table. So you'll notice in these three different solutions, we have trial 1, trial 2, and trial 3. In trial 1 and trial 2, we hold Ki constant, 10 mils and 10 mils. And then in trial 3, we double it. So that means now that you can kind of see how this table is going to start to get set up. We're going to use these variations in the volume, which is going to give us different numbers of moles in the final solutions, where we have basically a rate where it's at 1 concentration and then a rate where it's at twice that concentration. And then the same thing is going to be the case for the peroxydisulfate. We have a concentration that's based off of 10 mils, and then in one reaction we're going to double that, and then another reaction we're going to hold it constant. So you can see how we're going to kind of start to build our table. So the way that we're going to work this out is in this table we have volumes. We don't have concentrations in the final solution, right? So we're taking 10 mils of this 0.2 molar Ki, and then we're diluting it up to 40 mils. So when we do that, when we take some concentration times some volume and we put it into a new volume, that's called a dilution. And we're going to use the dilution equation M1V1 equals M2V2 to calculate the concentrations in the final reaction. So let's do this, for example, for solution 1. So we want to know what is the concentration after all is said and done, meaning we take this 10 mils of 0.2 molar Ki and we put it into 40 mils. What's going to be the concentration in that 40 mils? So we take 0.2 molar, we multiply it by the volume in 10 mil, which is 10 mils. So we take 0.2 molar, we have 10 mils of it, and then we dilute it to the reaction mixture, which is 40 mils. So if we solve for the molarity in the reaction, we get 0.050 molar Ki. Now remember, we can do this with mils because the units are going to cancel out anyway. You can convert this to liters if you want, but when you use M1V1 equals M2V2, you don't have to convert this to liters because the units will cancel. And you could do this for all of these. So you could do this for solution 1, solution 2, solution 3. You can get the concentration for Ki and the concentration for the peroxydisulfate using M1V1 equals M2V2. And you should practice that because this is something we could ask you on the quiz. So make sure that you are, don't just take this for granted. Even though we kind of do the math for you, you should know how to do M1V1 equals M2V2 for the quiz. So now in trial 1, we figured out from doing our M1V1 equals M2V2 that we have 0.050 molar I minus. If you do the same calculation, 10 mils times 0.2 molar into 40 mils, we get the same concentration of peroxydisulfate. So you can see here for trial 1, we have equal concentrations of the S2O8 2 minus and of I minus. And we calculated our rate back from the previous thing. We made our graph, we got the slope, we divide the slope by the volume to get a rate in molar per second. Now this value is going to be slightly different from the value that you guys get. And that's just because I graph my data using a graphing software, and that's going to give me a more accurate result. When you guys graph this by hand, you're going to get slight differences. So make sure that, when you do your graph, that you're paying attention to that. You don't necessarily have to get exactly the same number I did. It's going to be close, but not exactly perfect. And then what we did was, so we have this first data set, and we're going to repeat all of this entire process. So we're going to create a second trial where we have where we take for solution A, we're going to take this set, and then in solution B, we're going to have twice as much of a concentration of the S2O8 2 minus. And then in that trial, we're going to set it up. We're going to mix A and B together. We're going to have our aliquots of S2O3 ready to go. And we're going to measure how quickly it takes to get to the blue complex over time. And then we're going to do the same thing for trial 3. And then we're going to calculate the rates for each of those. So now if you look at the custom data sheet that we created for you guys, you're going to see exactly that. So in trial 1, we observed this one. This week we actually physically watched it take place. And you saw how the data points were generated. Each time represents a time where the solution turned blue. And then up here you can see that the calculations were already done for you in the textbook for the concentrations. They did M1V1 equals M2V2. So now when we set this up with a slightly higher concentration of S2O8, you'll notice that the reaction speeds up a little bit. It goes from 128 seconds for the first color change down to 59 seconds for the first color change. And that makes sense. We have a slightly higher concentration of one of the reactants. And the same thing is the case for when we have a slightly higher concentration of I minus. We have 64 seconds here instead of 128 seconds there. So you can see that increasing the concentration has an effect on these rates. These ones go quicker. And now your job is to plot these out on graph paper and to come up with the rates. So what you're going to do is you're going to take these data points and these moles consumed, you're going to create plots, and you're going to get the slopes, and then you're going to divide the slopes by the volumes to get the the rate of the reaction. So you're going to get the rate for solution 1, solution 2, and solution 3. Those are your 3 different trials. And then you're going to answer these questions. So how does doubling the concentration of I minus affect the rate of the reaction? How does doubling the concentration of S2O8 have on the reaction? Then you're going to write a rate law that is consistent with your data. So you're going to decide, hey, basically what you're doing is for 2, you're telling me what is the order for I minus. For 3, what is the order for S2O8 based on the table that you create? And then you're going to write the rate law from that using the method of initial rates. And then finally, you're going to use, you can use any one of the 3 trials, the rate that you come up with, and the concentration data to calculate the value of K. Now, there's one other little part of this, and this is the preliminary experiments. And you can look at the video to see this. So, what are the solutions that what are the color of the solutions that contain K plus and I minus? So, if you look back at the video, K plus and I minus are in solution A, which is a solution that's sitting on the stir plate. So, is that solution colored? And if it is, you can write that down here. But you can see from the video right away when the reaction begins, when you have K minus and I minus that are sitting there, you can tell if that is colored or not. And then the next part is write the color of the starch I2 complex, and we know that this is a blue color. We saw that. So the reaction kind of starts off colorless, and then it goes to a blue color. Hint, hint, wink, wink, nod, nod. But this is all important because this is how we set the clock up. So that's how you're going to fill out the data sheet. Now let's talk about the graphing. So I know I talked about some of these things with the graphing already, but I really want to make sure you guys get the graphing right, because a lot of students lose points in the graphing and it's sort of needless. So the graph paper that you're going to have are on pages 221 to 223. So the first thing I want to point out is you need to have 3 graphs. Even though I graphed the data out for the first trial just to show you what the graph should look like, you still have to graph it. So you're going to have a graph for trial 1, a graph for trial 2, and a graph for trial 3. Now, for some reason, the textbook has these wonky labels on it. I don't know why they did this, and it's kind of crazy, right? They give you this whole big piece of graph paper, and they want you to graph it in like 1/3 of the graph paper. It doesn't make any sense. So you could just cross all that out and get rid of it. You can just write your labels right over it, and you can orient the graph paper however you want. I think doing it in sort of a landscape makes more sense, where you have time on the bottom and the moles of the S2O82 minus on the top. But definitely don't use the labels that are already on there. That's not going to be good. So cross those out and relabel to better fit your data. So you want to make sure that your time axis, like so for example, let's just go back to our data. So this thing is going out to 765 seconds. So you're going to want to set this thing up so that 800 seconds or something like that is going to be out here to about 3/4 height. And the same thing goes for the peroxydisulfate. So the peroxydisulfate goes up to about 4.8. So you're going to want to make sure that the top of this graph is at like 5 or 6 or something reasonable like that, so that your data points are going to span most of the graph paper. And then you're going to write down your increments, and you're going to label the graph so that we know what you did and that it all makes sense. And you're going to have time in seconds, moles of peroxydisulfate on the vertical axis. And one thing I want you to make sure that you do is make sure that you put an explicit point at 0, 0. Now, the reason why you want to do that is because when you use your ruler to draw the best fit straight line, the line has to go through 0, 0. So no matter what happens with your line, that line's got to cross that 0, 0, or else you're going to get points taken off. And remember, that's because at time 0, none of the peroxydisulfate has been consumed. And then you want to make sure that you measure the slope from 2 distant points. So don't use the actual data points, but take the best fit straight line. Look to see, like, let's say the best fit straight line crosses right over here. That's a very nice, convenient data point. That's a nice, convenient point to use because you can just read off those 2 points off the axis where it crosses kind of a nice grid line crossing. So that's what I mean by being convenient. And don't use the actual data points. So that takes you through the experiment. If you have any questions about how to do this experiment, this one is a little bit more complicated. So you may want to jump in and, if you have any questions about it or you need any explanation, your instructors are happy to answer those questions. So, feel free to contact your instructors if you have any questions. And, take your time on this one. The theory behind this one is really important. So one thing I want to mention for the quiz is you should know what each one of these things is doing. So, for example, on a quiz, we could ask you, what would happen if we doubled Ki, for example? What would happen to the rate of the equation, the rate of the reaction? Another thing we could ask you is something to the effect of, what would happen if instead of using 0.4 mils of the Na2S2O3, we used 0.8 mils of the Na2S2O3? So you should know what each one of these things are doing and how it affects the clock reaction. So what would that do to the time it would take to get to the blue adduct? So don't be fooled, don't be kind of lulled into a false sense of security with this experiment. You really have to know everything from what's going on with these reactions, right? So what kind of reaction is this? This is a redox reaction. That's important to know. But then what are each one of these things doing? What is the S2O32 minus doing? What is the S2O8 doing? What is the I minus doing? What is the I2 doing? What is the starch doing? Make sure you understand all of that and how it actually affects that color change and when the color change takes place. Okay, guys, so take your time on this one. Really look it over in the lab manual. If you have any questions, ask your instructors. And, make sure that you prepare for this one for the quiz, because a lot of times students kind of, when it comes to quiz time, they don't really know what we might ask. But I'm kind of telling you now that it could be related to a lot of different things in this lab. So you should really spend some time thinking about what would changing any one of these things do to the outcome of what we see in this video. Okay, and then so if you're going to finish up the data sheet, you're going to have 3 graphs plus the data sheet. All filled out, so you're going to have answers to all these questions, and you're going to have your graphs, and that you're going to submit on the date that the syllabus says for this experiment.